I've been asked many times about how to design and size cables, and since I'm currently working on a substation SLD where I need to size several low voltage and medium voltage cables, I thought this is the perfect opportunity to create a video and walk you through a real-world cable sizing workflow. Just a quick note before we start, this is a rough design, not an official cable design package, and we're not issuing any formal documentation from this calculation. It's purely for learning and practical understanding. In this video, we'll focus on a 400-volt LVAC cable from a 100 kilovolt amperes transformer, and in the next video, we'll move on to a 20 kilovolt MV cable design step by step. Before we start, just a quick note, we're not using those basic cable size schedules here. They're too simplified and don't consider real-world factors like derating, installation method, insulation type, or short circuit capacity. If you're working in industrial design or utility-level projects, you need something more reliable, so we'll follow a proper engineering workflow instead. Step 1. System Specifications Review. Before we calculate anything, we need to know exactly what kind of cable we're designing. In this step, we need to know about the load type, supply, and general requirements. So here, our system is a 400-volt, 3-phase, 50 Hz LV supply coming from a 100 kilovolt amperes transformer. The cable length is about 40 meters, and it's feeding an AC distribution board. Before we move on, we also need to understand what kind of load this cable is feeding. This matters because different loads behave differently, especially when it comes to power factor, harmonics, and how the cable heats up. If the load is a motor or something highly inductive, the power factor will be lower and the current characteristics change. If it's a data center or anything with lots of electronic equipment, we need to consider THD, harmonics, and sometimes even oversize the neutral. In our case, the load is normal. Substation internal loads like control, protection, and general loads. Nothing special, just a standard AC board with a power factor around 0.96. So we don't have to worry about harmonics or special derating. It's a straightforward load, which makes the cable sizing simpler. Next, we choose the general cable specification. For substation or industrial work, we normally go with copper conductors, XLPE insulation, PVC outer sheath, and SWA armor if the cable needs mechanical protection. Voltage rating is typically 600 volts or 1 kilovolt, and we use a 4-core cable, 3 phases plus neutral. This step is basically setting the rules of the game. What voltage we're dealing with, what environment the cable is installed in, and what type of cable the project specification expects us to use. Once these specs are clear, we can move on to the calculations. Step 2 is calculating the rated current. But which current? We're not talking about the load current here. We're talking about the current our power supply can deliver, which in this case is the house transformer. So the first thing we look at is the transformer's rated current, because that tells us the maximum current the cable might ever see under normal conditions. But that's not the whole story. We also need to consider the protection device feeding this cable. In our case, we're using a 160 amp MCB, and our transformer is rated around 144 amps. So I'm going to size the cable for the worst case scenario, not just the normal operating current. And here's why. A cable is one of the most critical components in any electrical installation. If something goes wrong, a fault, a protection failure, a delayed trip, the last thing you want to be damaged is the cable. Because if a cable fails, it can cause fire, damage the entire site, shut down the control room, and replacing it is extremely hard, expensive, and disruptive. So we always design cables to be very durable, even under fault conditions. Even if the relay, fuse, or breaker doesn't operate immediately, we want the cable to withstand the fault long enough for upstream protection to trip safely. Now let's calculate the rated current of the transformer. This is the starting point for almost every LV cable design because the cable must safely carry the full load current under normal operating conditions. We have a 100 kilovolt amperes, 400 volt, 3-phase transformer, so the rated current is, when we plug in the numbers, so the transformer delivers roughly 144 amps, and for design purposes, we round it to 150 amps. This gives us a clean, safe working value. In the other hand, as our MCCB rated for 160 amperes, our design current will be 160 amps, and we'll use this value for the next steps like short circuit checks and voltage drop. Step 3. Short circuit current calculation. Now that we know our rated current, the next step is to check how much fault current the cable might experience. This is critical because during a short circuit, the current can rise to tens of times higher than the normal operating current, and the cable must survive that stress without damage. So, step 3 is all about calculating the short circuit current at the cable's origin, usually at the transformer terminals. We start with the transformer's data. Our transformer is 100 kilovolt amperes, 400 volts, and has a short circuit impedance of 4%. That impedance limits the fault current. The formula is where ISC is short circuit current, I rated is rated current of the transformer, and ZPU is per unit impedance in decimal form. Plugging in the numbers. So, the initial short circuit current at the transformer terminals is about 3.6 kiloamperes. In short, step 3 tells us how much current the cable must handle for a few seconds during a fault. We'll use this value in step 4 to verify that the cable's cross-section can withstand the energy released before protection clears the fault. When we simplify the transformer's equivalent circuit, we often ignore the magnetizing branch, the parallel branch that represents core losses and magnetizing current. Because of that simplification, the calculated short circuit current tends to be slightly higher than reality. So, to make the result more realistic, we deduct about 10% from the theoretical value. ISC adjusted is 0.9 times ISC. For your case, that means the effective short circuit current at the transformer terminals is approximately 3.24 kiloamperes, accounting for the neglected parallel branch. The cable length, 40 meters, adds resistance, which slightly reduces the fault current at the far end. For LV systems, this drop is small. Step 4. Cable selection from OEM manual and product schedule. At this stage, we move from theoretical calculations to real-world product data. We consult the OEM manual or manufacturer's cable schedule to identify a product that meets our design requirements. Process overview. Cross-reference manufacturer data. Use the product brochure or schedule to extract the correct cable size and type. Check rated current. Confirm the cable's nominal current rating meets or exceeds the load current. In this case, derated currents are already provided for different installation types, so we don't need to apply additional derating. Verify short circuit capacity. Ensure the cable can thermally withstand the calculated fault current from step 3. So I'm using Elan cables for this project. I just go to Products, Filter by Cable Type, and the first option here is the closest match to what we need in this project. You can see the general specs here: number of cores, insulation type, temperature rating, all the usual details. I'll skip the dimension table and go straight to the electrical table. This is the rated current. and I'm selecting the installation type in conduit. Here's the short circuit capacity as well. As you can see, 4 times 95 is the best fit. The current rating of 185 amperes is above our 160 amperes requirement, and the short circuit capacity of 8.9 kiloamperes is higher than the transformer's fault level, so it meets all the criteria. We talked about derating, but what is this exactly? Derating is the process of reducing a cable's nominal current carrying capacity to account for real installation conditions that make heat dissipation less efficient. Manufacturers publish derated current values because cables do not operate in ideal laboratory conditions. They operate in soil, ducts, trays, groups, or high ambient temperatures. Derating compensates for factors such as installation method, direct buried, duct, tray, conduit, grouped circuits, soil thermal resistivity, ambient temperature, depth of installation, number of circuits in proximity, thermal insulation or restricted airflow. When any of these conditions increase the cable's operating temperature, the allowable current must be reduced to prevent overheating. This reduced value is the derated current, and it represents the maximum safe continuous current for that specific installation scenario. Example of derating. Imagine a cable that has a nominal current rating of 200 amperes in ideal laboratory conditions, free air, perfect cooling. But in real installations, conditions change the way heat is removed from the cable. Let's say the cable is installed direct buried in soil, and the manufacturer states, derating factor for direct buried installation, 0.85. This means the cable can only carry 85% of its nominal rating under that installation condition. So the derated current becomes I derated is I nominal times 0.85. I derated is 200 times 0.85 equals 170 amperes. What this means, even though the cable is rated for 200 amperes, in your installation, it is only allowed to carry 170 amperes safely. This ensures the cable does not overheat due to soil thermal resistivity, burial depth, or reduced cooling. Step 5. Voltage drop calculation. Now that we've checked the rated current and short circuit capacity, the next step is to make sure the voltage at the load end is still within acceptable limits. This is where voltage drop comes in. Every cable has resistance and reactance, and over a certain length, that causes the voltage to fall between the source and the load. If the voltage drop is too high, motors can struggle to start, equipment can misoperate, and protection settings may not behave as expected. So we always check that the voltage drop stays within the limits set by the standard or the project specification. In practice, we don't calculate voltage drop from first principles every time. Instead, we use the manufacturer's data. Cable brochures usually give you a voltage drop value in millivolts per amp per meter for each cable size and type. For example, let's say the OEM manual gives us a voltage drop of 0.8 millivolts per ampere per meter for our selected copper XLPE 4-core LV cable. We already know our design current is 160 amperes and the cable length is 40 meters, so the voltage drop is 5.12 volts. On a 400 volt system, that's 1.3%. That's well within typical limits, often around 3 to 5% for LV feeders, depending on the standard and project requirements. So from a voltage drop perspective, this cable size is acceptable. If the voltage drop had been too high, we would have had two options: increase the cable size to reduce resistance and reactance. Review the route or length to see if we can shorten the run or change the installation. In short, Step 5 confirms that our chosen cable not only carries the current and survives faults, but also delivers a healthy voltage level to the load under normal operating conditions. Alright, that wraps up the LV cable sizing workflow. We started from the system specifications, calculated the rated current, checked the short circuit level, and finally selected the cable using the manufacturer's electrical table. As you saw, the 4x95 cable meets both the continuous current requirement and the short circuit capacity, so it's the correct and safe choice for this feeder. In the next video, we'll move on to the MV side and go through a full 20 kilovolt cable design process step by step.
I'm a master's level electrical engineer based in Dublin with over 10 years of experience in medium voltage system design and substation protection. And this is Exa Power Lab, where I break down electrical engineering, product comparisons, and practical insights. Thanks for watching, and I invite you to check out the other videos on the channel for more.